This video is on solid of revolution, and here I have a yellow region right here, and I want to revolve it about a line y equal to 2, and then find the solid of revolution. And so this yellow region right here is bounded above by the graph f of x equal to 2 times the square root of x plus 2, and then below is by the line y equal to 4, from 1 to 9. And then here's the axis of revolution. So we want to revolve this region right here about this line y equal to 2. And when we do that, then this is what the solid of revolution would look like. And so it's a solid with the hole in the middle, and this hole is just a cylinder. And this cylinder has a height of 8 and a radius of 2. And so to find the volume of the solid with the hole, then what we can do is find the volume of the solid without the hole, and then subtract from that the volume of the hole, which is the volume of this cylinder right here. And so here's what the solid without the hole looks like. And so this is the solid without the hole, and here's the solid with the hole. And so we want to find the volume of this solid without the hole. And then to find the volume of this solid without the hole, again, what we do is we would divide the solid into many slices, thin slices, and then find the volume of each slices and then add them together. And so this is what the ith slice looks like. And so this would be the ith slice. And so let's go find the volume of this ith slice. And so the first thing I'm going to do is I'm going to divide the interval from 1 to 9. So this is 1 and this is 9 into n number of sub-intervals. And then the first value right here, let's call it x of 0, which is 1. And then we have x of 1, x of 2, x of 3, x of 4. And then eventually we get to the ith sub-interval, which is where this ith disk comes from. And then when we get over to 9, then this will be x sub n. And so let's say that n is 8, meaning we want to divide this interval right here into 8 sub-intervals. Then the length of each sub-interval would be 1, since 9 minus 1 over 8 is 1. And so the thickness of this disk is also 1. But if we divide the interval from 1 to 9 into 80 sub-intervals, then the thickness of each slice would be 0.1, or the length of each sub-interval would be 0.1. And so in general, the thickness of each slice would be 8 over n. And so let's denote the thickness of each slice as delta x. So for the ith slice, which comes from this ith sub-interval right here, and so right here, the x coordinate would be x sub I minus 1, and then right here, the x coordinate would be x sub I. Here's the x-axis down here. So right here, this is x sub I minus 1, and then right here, this would be x sub I. Now at x equal to x sub I, then f of x sub I is the distance from the x-axis up to the graph, meaning it's the distance from here to here. So right here, this is x sub I, and so f of x sub I is the distance from the x-axis up to the graph. And so therefore f of x sub I is not the radius of this disk, of this ith disk right here. The radius of this disk would be the distance from the x-axis up to the graph, and then minus 2. And so the radius of the ith disk would be f of x by minus 2. And then f of x is 2 times the square root of x plus 2. And then minus 2, then we just get 2 times the square root of x of I. And so for the ith disk, which is a cylinder, the volume would be pi times the radius squared times the height. And in this case, the radius is 2 times the square root of x of I. And so this is the volume of the ith disk. And if we divide the solid into n slices, then the volumes of n disks or n slices would look like this. This would be the volume of the first slice, volume of the second slice, and then volume of the nth slice. And then using summation notation, then we would have I running from 1 to n with the expression pi times 2 times the square root of x of I squared times delta x. Once again, this is the thickness of each slice, and then this is the radius of the ith slice. And then 2 times the square root of x of I squared is 4x. And so this sum right here, this is the volumes of n slices. And so the volume of the solid of revolution would be approximately this sum right here. And if we want the exact volume for the solid of revolution with no hole, then we have to allow n to run to infinity, meaning we need to divide the solid of revolution here into an infinite number of slices. And so when n runs to infinity, then we write it like this: limit of this sum right here with n approaching infinity. And when the limit here exists, and then we would define it as the definite integral from 1 to 9. 1 to 9. And then 4x, and then we have pi, and then we have dx. And then we just evaluate this definite integral right here. So the pi is right here, and then the integral of 4x would be 4 times x squared over 2, and then this will give us 2x squared. And evaluating from 1 to 9, when x is 9, then we get 162, and when x is 1, we get 2. And so the volume of the solid of revolution without the hole, with no hole, is 100 with no hole, is 160 pi. So here once again, here's the solid with the hole. Now this hole here is just a cylinder, and the height of this cylinder is 8, because we're going from 1 to 9. And then the radius is just 2. And so the volume for this cylinder here is just pi times the square of the radius times the height, or we get 32 pi. And so the volume of the solid with the hole will be 160 pi minus 32 pi, which is 128 pi. And that's the volume of the solid with the hole. And that's the end of the video.